Okay, let's start. Any questions, Wesley? So again, a reminder to go ahead. Yeah, so 4 to 4:50. So I will not do my office hours. I'll just. It's I was actually looking at my phone. So I think it's Math Science 5127. So neighboring building 5127. I don't. No. So tomorrow's purpose is that I will go over some of the topics that my students have contributed. Okay. If you already know some project that you want to do, you don't need to come. Okay. Then you just come and speak with me and just affirm. Otherwise, if you are like looking for project ideas, then come for that. Okay. So that's the only purpose. If you still want to meet me during office hours, then let me know, and I will. Basically, I'll be in my lab after 12:30 onwards. Those of you who don't know where my lab is, it's 1762 Bolter Hall. So, I'll be, basically prior to the discussion section, I'll basically be in my lab. So just come over there. But if you don't have any idea on projects, then come to the discussion section and I'll walk through some topics, kind of give you a rough sense of what we are looking for, and then I can help you hook up with the students who are mentoring, or actually Leon, who's at the back, knows everyone, so he would be a good resource for you to follow up on a specific project. Okay. So again, those of you just drifted in, discussion section tomorrow, and it's again Math Science 5127, I think. Yeah, Math Science 5127 at 4 p.m. Okay, so we'll sort of continue on kind of giving you a sense of what goes on in embedded system platform, and kind of really look at the software side of the story, how software gets organized, and then kind of the following set of slides, which I have also put on the on Piazza, go into the scheduling, which is kind of a key component behind the way software gets organized. But this particular lecture 3 kind of really focuses on how software is organized, kind of in broad terms. Okay. So again, this picture we have seen before, that many platforms really make use of programmable CPUs, sort of MCUs, or even in some cases standard microprocessors. So what we are really looking for is how does the software for these get written. Something that I emphasized early on in kind of the last slide set was that the CPU just happens to be one of the choices. You have to realize your algorithm. Oftentimes in many systems, it may be some sort of a more specialized processor, or perhaps not even a processor. It may simply be some custom chip. Although I would say like close to 100% of the systems would have some processor, even if it is not doing the heavy lifting of data processing. Most of our systems tend to be networked, and perhaps the easiest way of making your embedded system networked is to use some standard off-the-shelf operating system which already has a TCP/IP stack, lets you hook up to the internet, because creating all of that from scratch is problematic, very error-prone, particularly things such as cryptographic routines and all are very hard to get right. So kind of the general advice is don't implement yourself. For that portion, kind of use something that already exists. So almost every system would have that, and I think Linux has penetrated very heavily there, but there are other commercially supported operating systems as well. Okay, so before we dive into it, one thing to bear in mind is that the software development cycle for embedded systems differs considerably from kind of what we tend to use on our normal computers, where commonly nowadays you just would either have a local locally running sort of program, and you compile and run it and all, or increasingly kind of you log into some remote server, oftentimes even perhaps through your browser, and there is some virtual machine running, and you can run your code there. But here, you ultimately have to produce the code which actually goes onto the hardware device. So you start with some source code. You will either have a native toolchain, and that gives you an x86 binary, and if it so happens your embedded system is also an x86 system, perhaps even running Linux, then you are done. You can literally take the same program and kind of move it there. More generally though, you will have to go through some sort of what is called as a cross-compilation toolchain, which basically means that it's a compiler which produces code for a different processor than the processor on your local machine. So for example, since many embedded systems use ARM, so it could be a cross-compilation toolchain which runs perhaps the same compiler, let's say GCC or Visual Studio or whatnot, but it's producing code for ARM, and then at the end you are going to get sort of a so-called executable file, a binary file, and you're going to move it to the hardware platform, and variety of ways of doing it. In some cases, you're going to use some sort of a special hardware gizmo to download it, so kind of some sort of a programmer. But in case of embed, for example, it is through that USB pathway that I described last time. And if your embedded processor is somewhat more capable, maybe it itself is a Linux based machine or iOS or whatnot, then there might be an app store, or you might SSH into it and put the file there. But those kind of capabilities are perhaps more for the high-end things. For otherwise, typically it would be some one of the first two. In many systems, you also have to change the firmware, the code that is sitting on the device remotely. So over-the-air updates are quite common. So you're probably all used to sort of different ways to load firmware onto your cameras and home gateways and stuff like that. So there are a variety of ways. Just to give you a sense of what happens in a typical, when you write a program, so you start with writing whatever, let's say C code or C++ code. So when you compile, all that happens is it compiles the code, that part of the code that you have written, but that in itself is not sufficient. You also need to link it with the libraries that you might be using, and that's called the linking phase. That those libraries might be something that you provide, or more typically built into the operating system. Commonly on our laptops and all, these libraries are so-called dynamically linked libraries. So all your code has is kind of a reference to them, and then when you actually run the program, kind of the operating system takes care of things. In case of an embedded system though, the libraries need to be truly linked in, so that the code corresponding to the library is also brought into the same executable binary that you are creating. And in that process, it has to figure out where to put the library code, where to put your code, and at the end of the day, you get a file in which there is code, there are sort of some portion where all the constants that you have are residing, and then instructions as to where the stack is, where the heap is. Everyone knows what heap refers to in a program? No? Anyone knows what a heap is? Nope. Nope. Okay, so there are two ways you can have data or space for data in your program. One is you declare it as part of your program statically. So let's say you need there is some structure or class, and so you just declare, and I say I have a variable x of that type. Okay, so when you're compiling, it sets aside space for it as part of the address space, and that goes into the area where the variables reside. Okay, and in fact there are again two subcases of it. There are variables that you have which are global to the program, so they reside in a global part, and then there are variables which are local variables, like when you enter a function and you say int x inside the function. Lifetime of that variable is only during when the function is executing, so the space for that gets put where? Louder? Yeah, stack. So when you call a function, then it basically allocates the space for all the variables that are needed for that function call on the stack, and then you kind of nest through this. So that's the second place variables go. But the final one is when you do, in case of C, malloc, in case of C++, new, right? So those are called dynamically allocated things, right? You are making a request to the underlying system that, hey, I need space for this, allocate it to me. And sometimes you get back a null, in which case you have a problem. That stuff goes into a pool of memory that is maintained by the operating system, and that's what is called as heap. So these are the three places where data resides. Well, there is a fourth one also. If you have constants, then they could be sitting in, you can think of them as really kind of akin to the code, it's fixed. So constants, global variables, local variables, that is variables which are within a function, and then finally these dynamically allocated variables which go into the heap and which you need to free, and if you forget to free, then you're losing memory. In languages like Java, they take care of freeing the variables for you. In languages like C and C++ or Objective-C, you are responsible for freeing them up. In embedded systems, since memory is very tight, so generally dynamically allocated variables are kind of a bad idea, because really for your car or robot or a spaceship, it's not an option to say typically run out of memory, can't do anything, right? I mean, so memory usage and all has to be very carefully analyzed so that running out of memory doesn't happen, or if it does, you have a escape route around it. Okay, so compilation is followed by this linking and all, and then the final phase is loading, when you are actually moving the program into the physical memory, and then you're kind of deciding where should what should go there. And when you're writing a piece of code in a file, when it gets compiled, it's compiled as if it's starting from, let's say, address 0. But then when you are linking, there are multiple different pieces of code, some from the library, some from your own files, are coming together. So obviously they cannot all be from address 0 or whatever the fixed address where the code starts. So then code has to be moved around, and in the process, depending upon the type of CPU you have, you may need to make changes to the code also. All of it is done by the compilation chain. In case of embedded systems, typically at the end of it, you have a single binary, you put it into the memory and reset, and you are good to go. But oftentimes you need to update only a part of the firmware, part of the code which is there, in which case it would be kind of wasteful to compile kind of a new firmware from scratch and then re-upload the whole thing, although that's what is commonly done. But in many systems you'll find that you can modify much of the firmware is unchanged and you are modifying just part of it. So a lot of effort goes into kind of making dynamic updates more efficient there, so that the update process is fast, takes less time, less downtime. If you're updating something which is controlling, I don't know, let's say AC in your home, then you want the downtime of that process to be as little as possible. So a lot of work goes into kind of making that process efficient also. But kind of backing up, kind of the main thing is that you're relying on these tool chains which create potentially executables for totally different processor than the one you are running on. Like for example, the Cortex M4, which is used in these embedded devices, or Cortex M series. Your laptop obviously is Intel, more likely than not, so totally different. So compile chains. It used to be that these cross compilation tool chains used to be kind of costly industrial thing, but there are very good open source things which are very well done available now, in particular kind of GCC, which is a GNU compiler, and LLVM, which is another open source compilation setup, very easily downloadable, so for all the three common platforms, so very easily done. In many other cases, since even this level of installation and all can be a pain for some users, you also have cloud-based options, and Mbed is an example of that, where you log on into a browser and then you write your code there, the compiler is there, they've taken care of it, and then at the end when you compile, they basically just download the binary for you. You miss out on lower level control over the process because all of this stuff is happening on someone else's machine, but for a lot of work this is perfectly fine. So the typical cycle then looks like: you write code, you compile it, you download the device, you test it, and kind of repeat the cycle. But oftentimes this is kind of insufficient because, as I mentioned last time, you do not have a easy way of debugging code running on these embedded devices. It's usually not even a screen, and it's very hard to debug just with those LEDs, and you can't go around just probing things all the time. So a very common thing which has emerged in kind of last decade or so is ability to simulate. And what works to your advantage is that your computers are a lot faster than the processors on the embedded systems. Right there, perhaps you have a 10x, 100x advantage in terms of simulating the platform. So there are several different types of simulators that are out there, but you could think of them along kind of couple of different dimensions. So there are simulators which simulate the processor or the MCU, and or in some other cases just simulate the whole system in its entirety. So like, let's say it's my phone, you can imagine simulator which simulate the ARM processor inside the phone, or simulates the whole phone, or anything in between. And the other thing is, at what level of detail are you simulating at? So there are simulators which literally simulate the circuit at the inside the chip, so they are clock cycle accurate. Then there are simulators which simulate the instructions in the processor, but they don't provide you clock cycle level accuracy. So the program will run, but it may behave very differently than the processor, which is actually on your chip in terms of how much time it is taking, the relative number of clock cycles. It's not timing accurate, but it does get to use the same program that you would be running on the actual device. And then finally, there are function level simulators, and what they do is they try to mimic high level functions. So like, if you have a function to do some computation, some FFT or something like that, perhaps it will just provide you equivalent function but running on your local host machine, okay, and implemented as a piece of host code. So variety of approaches: code blocks which are mapped to equivalent native code. So you take functions and then you just, as if you compile them for your local machine, and you just use those. Binary instructions executed on a virtual target processor. So in this case, what you do is you implement a virtual processor which can execute the instructions of your target processor, and that's what you are mimicking. And then finally, you could run a circuit simulator which is simulating the gate or transistor level design, and what would, like, obviously this is the most accurate and this is the least accurate, and kind of, so fidelity kind of changes, but also imagine the bottom one is the slowest, and depends upon your needs. So if you are in the business of designing a processor or kind of creating a system on chip yourself, perhaps you might even do this third level of design, but very slow. Usually at this level, if you're simulating, you might even make use of FPGAs. That is, you will take your processor's, your chip's design, you're going to put it onto an FPGA, and then you are going to, instead of running at gigahertz, maybe you are going to be running at tens of megahertz. Or you might do a highly parallel simulation. Maybe you might be able to run it in terms of a few hertz. For most common usage though, one of the other two things, and these first two technologies are pretty advanced because we also need it for virtual machines in our normal computing setting also. So there are good techniques that have emerged for simulating processors, In fact, the whole Java language, for example, is based around the concept of a virtual machine, JVM. There are great open source realizations of processors. There is something called QEMU, which emulates a variety of different processors as an open source package used very, very widely. There are very broadly sort of two kinds of processors that we encounter. One are these really tiny 8-bit, 16-bit type things, and they are really very simple processors, so very easily simulatable. And then you have these 32-bit type things, which sort of both the devices we are using in the class are, and they obviously are more complicated, and their software systems are accordingly more arbitrary also. So typically for 8-bit, 16-bit type stuff, what you will find is that either you would be programming it bare metal, as in you will write the code and the very first instruction the chip will execute would be your code. So you'll be responsible for writing everything from kind of initial booting and stuff like that. Very commonly done that way. But there are also lots of open source and commercial packages which take care of that initial stuff. They kind of are very simple operating systems, and then you write kind of just user level code. So if, for example, if you have ever programmed Arduino, for example, that's an example there. It kind of gives you a very it takes care of all the low level details, and in Arduino all you write are two functions, the initial setup function and then this loop function, which basically it just repeatedly kind of goes through, and all the other stuff under the hood is taken care of by the Arduino runtime. The whole boot up process and all is a lot more complicated in these 32-bit things. So accordingly the operating system kernels and all are far more complicated. Usually the processors out in the first category, everything will be sitting in a flash memory, whereas in the second category, like your Raspberry Pi and all, the code is brought into the DRAM. There might be a large amount of memory and kind of running from that. Back to simulating these processors. So QEMU, which I mentioned, is kind of a very dominant piece of open source software, and even a lot of commercial packages are built around it. So what QEMU does deep down is it has, depending upon whether you are using it for x86 versus anything else. So if you're doing it for anything else, like let's say an ARM processor, it literally mimics instructions of an ARM processor. So somewhere deep down in QEMU there is code which examines the instruction and then as if conceptually mimics the processor for that. Kind of slower than what things would otherwise be. So for x86 it takes a different approach, because if it is already running on x86, so there is no need to interpret those instructions again. So it basically translates, takes that piece of code and just runs it natively on the processor, so a lot faster. You'll find a lot of simulators now available for different kind of systems which use QEMU or something like QEMU at their heart, but then they give you an overall system level simulation capability. So when iPhone had originally come out, its development environment included a pretty nice iPhone simulator. So sort of you're developing code in Xcode, which is kind of Apple's IDE, and then there was a separate program which would basically pop up a whole screen and all. And the nice thing was that whatever code you're compiling, you can send it to the simulator, execute it, you would see all the, as if all the things in a phone. Moreover, it could even make network access, and also you can have a program running in the simulator which is reaching out to, let's say, some website and downloading stuff. And this kind of capability is pretty routine. Later on, when Android came, it had something similar. Android was actually, their simulator was initially at least based around QEMU. The same concept in recent years has made its way to more routine embedded devices. So for Arduino, there is a simulator. So if you basically, when you run it, it kind of gives you a fake Arduino compatible board, and you write your code, and you can attach components to the pins, and it can blink LEDs and stuff like that. So without having a real Arduino, you can do things. And a few months ago, Mbed did the same thing. So there is now an Mbed simulator also. And if you go to the Mbed simulator, having networking problem. Okay, EduROM is giving me problem. Anyway, so what it does is it shows you an Mbed board, and you can write your code and kind of run it there. You can attach certain simple components, the pins on that fake board, and kind of do a lot of the simpler stuff right in your browser basically. So these kind of simulators are getting pretty sophisticated and make life a lot easier. Second thing, so besides this cross compilation with simulation, second thing is the world of embedded programming is what is often referred to as bare metal programming, and kind of the idea being that you are often writing code which directly talks to the hardware, as in makes use of peripherals and all on the chip. It's usually when you are doing general purpose programming, you're always kind of behind the layer of abstractions that the OS provides. If you need if you need to deal with time or location and these kind of things, you don't directly work with clocks or GPS. You kind of make use of some calls that the operating system provides. But when you're working with embedded systems, usually you may have some weird new hardware, and also you'll have to just directly dive into those details. So there is oftentimes there is no real operating system running, and even if there is, it may not be supporting your particular device. So you're effectively not only writing your application, you're also writing the code which is directly talking to that hardware. So code that reads and writes to registers and twiddles pins and stuff like that. So very important to become familiar with the hardware, because otherwise you will not be making use of the full capabilities. Third concept, interrupts. So at the heart of these embedded systems, these are, since they interact with the external world, they are often operating in the mode where when something interesting happens in the surrounding hardware or the external world, then the software does something. And that interaction is often conducted using interrupts, which basically, I'm sure you would have encountered these in some undergrad class, but basically some external world kind of changes the state of some pin, and that causes the processor to sort of divert from what it was currently executing and then run the so-called interrupt handling. So when you are dealing with these kind of events which are happening on the pin, one way would be the so-called polling approach, where you write a code which is repeatedly reading the pin status or the status of a register, and then when it sees some appropriate change, takes an action. The con of this thing is it's very wasteful, and you are kind of just burning power just monitoring that pin. So interrupts are what are used at the low level, where the processor have some sort of a hardware unit which kind of monitors it, and when the pin status changes, then it stops executing the instructions and then instead does something which essentially results in calling the so-called interrupt handling function. So all of that magic is hidden from you. Now in normal general purpose computing, you never write an interrupt handler. Although interrupts are there on your processor, but they are all being handled by the operating system and the device drivers that exist there. But when you are writing code in this bare metal type scenario, then you'll be writing ISRs yourself. So in Mbed, for example, you would see that it lets you write a function and designate it as an interrupt handler for a particular interrupt. Arduino has the same programming model, so you can write your own interrupt handlers and sort of attach it to these events which are coming. Now, there are certain restrictions on these interrupt handlers because they are not quite like your general purpose code. They are running whenever the event happens. It kind of interrupts the flow of your normal program, and then it has to execute those functions. So one very important thing it has to keep in mind is that when the interrupt is over, the original program should be able to resume as if nothing happened. As if right, it should resume wherever it was, which could be any place because the interrupt can come at any time. So any registers which were in use by the main application should be saved and restored as part of your interrupt handler. Any registers. Okay, now which registers are in use by the applications are decided by the compiler. So all compilers have some sort of an associated thing, like they would say these registers are in use, and then if you're using an operating system, then sometimes for like Arduino, let's say, so they may say when your interrupt handler is called, we already take care of saving some registers, so you don't have to resave those, but the others you have to. So what this means is you have to understand the compiler that you're using, and you have to understand the processor that you're using, because some of these things differ from compiler to compiler also. So save the register, do whatever you're doing in the interrupt, and then before getting out, restore the values. Okay, so that's very important. So when the other thing is that since you are disrupting the main flow of the program, so oftentimes you'll have to make sure that the interrupts are kept very short. And then finally, it could be that you need some resource in the interrupt handler which the application is already using. Like for example, let's say you want to control some sort of device, but that device is already, the application was in the midst of using it, then your interrupt handler cannot really do it. So very commonly what happens with interrupt handler is that instead of actually doing work, you basically put a task into a queue and then you rapidly return, and then later on your application will go and examine that queue and then say, okay, now I can handle it. So we'll talk about it, but you have to deal with these interrupts very carefully, because otherwise your code can become kind of a spaghetti mess and all sort of difficult things can happen. So conceptually, then what happens in an interrupt is when the signal comes from the outside, deep down the hardware of the processor waits for the instruction that is currently executing to end. Then it pushes the program counter onto the stack so that it can resume. It pushes, then you have to make sure as part of the interrupt handler, push all the necessary registers onto the stack so that the state of the program is preserved. Then you jump to the interrupt handler. Usually it would be some sort of a table which will say for interrupt number 10, you jump to this function. So that's often referred to as interrupt vector. And then when you are done, you pop the program counter off the stack, and before that you also restore the active registers that you just saved. So all of that needs to be done. So interrupts. And a final thing, which much of the remaining slides in this thing are going to talk about, is that the reason we use processor in part is that we can share it among different software modules, right? Relative to hardwiring the logic, in hardwired logic you only run one application. The nice thing about processors is that at different times you can run different things. So you can share the same arithmetic unit and stuff like that across different things. So this concept of multiplexing a single piece of hardware, CPU hardware, across different software modules at different times is very important to get maximum utility out of processors. So there are many different ways you can conceptually share the CPU among multiple software modules. The one which we encounter most commonly is function calls or subroutines. So you are running some piece of code, and somewhere you will call a function which basically causes a jump to happen to the start of the code for that other software module, but you also preserve the return address where you called. So here I say call B, so you also save where you were in A, so you save the value of the program counter, you call B, and at the end there is a return instruction which, as you can say, jump back to the address that you saved. And this is why you need stack. So like if B were to call C, then you go one level deeper into stack, and any variables that B needs are declared on the stack, and sort of go through that process. So in this case, at different times, different software modules which are hierarchically organized are using the same piece of software. And the compiler typically would, compiler would define for you all sort of etiquette that the callee and the caller have to follow. So for example, compiler may tell you that the arguments that you pass to B should be saved in this manner, right? So typically compilers would say the first two arguments can be in the register, and the remaining arguments have to be put onto the stack because registers are relatively few. The compiler may also dictate that some registers it will save, A will save on its own, so that B doesn't have to worry about crashing. And any other register B before using has to preserve and restore. So there are all these kind of protocols which are defined, and again, one has to be aware. And people who write malware, you often hear about buffer overflow attacks in software. So what they really do is they make use of the way stack is organized and certain mistakes people make when coding to cause problems. So the mistakes people make is the following: that in this whole calling mechanism, we are assuming everyone is well behaved. But remember, stack is sitting in an area of memory where A and B both have access to it. And if I have C, it also has access to it. So in principle, B, if it were to be malicious, it could crash the portion of the stack where A was working with, right? Because it's just part of the same memory, there's no protection between. So if I can somehow compromise something out here, I can actually have full access to the stack. So malware typically makes use of those kind of capabilities, but for our purposes, the main thing that I would tell is this is, you can think of your sort of old-fashioned software calls as a way of sharing the processor with the property that obviously any one of them is running at any given point in time, and it has to be done in this structured manner that A calls B, B calls C, and then sort of you go back where you started. But that's not the only way software modules share processor. Another one which we all use a lot is we run multiple things on our computers, multiple applications, right? So multiple processes. And while it is true that nowadays processors have multiple cores, but not too long ago they were single cores. Your operating system basically moves the processor, shares the processor between multiple processes and takes care of things under the hood. So the OS is doing it. So OS at various times would say, hey, you stop running, now I'm giving the processor to B. And during that context switching from A to B, all the necessary state would be saved, and then when A is restarted, it will be stored. And this process is referred to as scheduling. That is, it's the job of the OS to decide when does which process get to run. And it could be based upon things like what is more important, who has a closer deadline, all those kind of things come into play, but we basically kind of give the illusion that A has a processor, B has a processor, but it's really time shared between them. And so threads within a single program or processes corresponding to separate program. And you can think of this that unlike the hierarchical stuff there, this is more symmetric. A and B don't even need to talk to each other. And they are running concurrently, so there is an illusion of parallelism, right? I mean, depending upon the OS, it could be all of A runs and then all of B runs, or maybe a few instructions in A run, then a few instructions in B, and then again a few instructions of A. How precisely that sharing is happening, you cannot assume anything, and therefore, if A and B need to coordinate, then you need to take special care. Okay, so all of that the OS provides assistance. And there is a third model which exists in many programming languages, less common but very important, and it's, like I said, it is in Python, for example, or Go, which is anyone heard of Go? Yeah, so it's from Google. It's actually by the same people who gave us C back from Bell Labs. When they moved to Google, they created Go, and it's kind of the, you can say, a better C is how I would describe it. Okay, so Go is really designed when you have concurrency as part of a built-in language feature, because nowadays we write things a lot where many things are happening. Embedded systems are one, and also things like web servers and all, they also have to handle multiple requests, and also Go is something which is pretty commonly used in science. Okay, so what these languages provide is something called coroutine. And the way coroutines work are the following. So let's say A is running, and someplace A will say resume B. Now the distinction between resume and call is the following. When I say call B, then B always starts at the beginning, and then it will exit at the end, and then return wherever I ended the call. In case of resume, when I say resume B, it starts B where I last left B off. So for example, the first call to resume B will start B at the beginning, and then B will run, and someplace B would do its own resume, like let's say let's resume A. So then I will return to wherever the resume B was done, and later on A does a resume B, B will now start where it left off. Okay, so if you think about it, here we need to remember something. Where was B or where was A? Whereas in function call I don't, because I always return back to the same place and I always start at the beginning. So these coroutines, while have this kind of symmetry, they have a process like symmetry. Both of them are advancing kind of together in parallel. But with the additional constraint that at any given point in time, only one of them is actually running. In case of threads or processes, if I had two processors, I could run A and B on their own processors. Whereas in coroutines, even if I had two processors, I can only run one thing at a time. Because when A does resume B, then it has to wait for B to hand control back. So only one of these guys, one of these modules is actively running at any given point in time. Whereas in the threads, both of them, given sufficient hardware, could run. So coroutines are kind of in the middle, therefore they are still sequential, much like function call. So they don't have the sort of, they give you an illusion of concurrency, but it's just an illusion because only one thing is active. But they're kind of symmetrically organized, which works great for a lot of different applications where, let's say, your system is supposed to do two different things. So protocols and all often get nicely organized this way. So coroutines are used in, like I mentioned, Go, and also Python has coroutines as well. Okay, so in terms of implementation complexity, subroutines or function calls are the easiest. They are the easiest because processors already provide support for them. Okay, they already have the call and the return and all, so you don't really need to do anything other than establishing some conventions by the compiler. Implementation of these two is increasingly more complicated. In case of coroutines, they are preferred by languages like Go and all because they are still a lot simpler than processes in terms of overhead. They kind of look like function calls, except for one change. You have to remember where the function last exited. So you just need one little piece of memory to remember where things were before you exited, and otherwise you don't need to do anything. Whereas here, when the operating system or the hardware decides that I'm going to switch from A to B, then I have to save all the registers they were using and then restore them. So there's a lot more overhead going back and forth in case of threads or processes. So far more complicated. So so these are the different ways software modules can work together. One of the, I guess, forever running debate, sort of say, in computing systems is that how should you organize this software? So in particular, how do we deal with the two things I have talked thus far in a way? So one is events. You have things coming from the outside and and your embedded system has to respond to it. There's a sensor reporting a crash is imminent, another sensor is saying user just pressed the key, a third sensor is saying a packet arrived over the network, and they could be coming in any order and often very close by simultaneously. So how does your system, how would you organize your software to do all of this? This is not the kind of software where you can simply sit in a loop and then say, did the user press the key, did the network packet arrive, is the car going to crash, and then repeatedly polling them. It will be pretty painful, because what if the user pressed the key and you decided to handle the key press, and meanwhile you didn't realize that a little bit later the sensor saying the car is going to crash is raising an alert, right? So you need some way to be able to do multiple things simultaneously. So events can arrive in an unknown order at arbitrary times and in parallel, and you need to write code which can handle that kind of thing. And that's a dominant sort of programming usage paradigm that your software will face when it's interacting with these external devices and all. So given these software modules that I presented, there are two common ways one can organize these systems, and there are kind of essentially two religions. People like one or the other, and the debate kind of goes on. One is to do it in terms of threads, and the other is to do it in terms of event handlers. And you could do in the same system both. You can mix and match, but they're deep down. So the thread approach says the following: I'm going to write my system as a bunch of software modules in the form of threads, and then if a thread needs to wait for something, I would have some sort of a function here, some sort of a API call which will say wait for something. So I can say, like, maybe the first thread out here, maybe some sort of a thing which waits for, which handles user key press. So it might say wait for the user key press, and then when it calls that function, control goes back to the operating system. The operating system will put this thread into some sort of a queue, designating, hey, it's waiting for the key press to happen. And then when the key press occurs, then this thread will become ready to run, and it can again take you to the CPU. The second thread may be doing, like the car crash sensor, so it might do the same thing. So somehow I will have some way to tell the operating system that I'm waiting for a particular type of event. And you'll find these kind of things even in your standard Unix or Windows or Mac OS X type APIs also. So they all, like, to give you an example, if you're writing C code and if you say read from a file or read from a serial port, read a port that you have opened, but if there's nothing on the port, what does the operating system do? It blocks you, and then later on when some character arrives on the serial port, then it will return. So it's called blocking IO, but basically what you're saying is that if there is already a character, give it to me. If not, wait for the event character arriving and then read it. So that's the left approach. You basically organize the software in terms of, you write it in terms of threads and you sort of wait for events of different types. You may even send events across threads. Okay, so like for example, I may have a thread which reads the data from the sensor, runs some FFT, and if the FFT indicates a particular frequency pattern is present, then it may send a thread to some higher level thread which can take some action on it. The other way of organizing software is in terms of what are called as event handlers. And event handlers are nothing but just functions. And then you tell the kernel that for event of type X, you should call function F1. For event of type Y, call function F2, and so on and so forth. And what the OS does is, deep down, the OS kernel is just sitting whenever these events arrive. It basically examines them in some order and then calls the corresponding function. And since these are just pure function calls, you don't need to do anything special because hardware already provides support for it. So the OS calls the function finishes its job, it returns. Very easy to organize, but do you see a drawback? Communication between these functions. Okay, so that's a good point. So it's a little bit painful to talk to these things. What you will have to do is you will have to have some global variables or somehow the OS will have to provide support for you to send a message from one to other. Okay. So valid point, but that's not the main one. There is a bigger drawback. Say it again, please. Right. Okay. So you are not. This is a less responsive system in principle, right? So in my example, let's say, precisely the example I was giving, the key press happened, corresponding event got called, but that key press processing takes a long time, and meanwhile that more urgent event arrived. But since it's a function, I'm going to finish and only then handle the next thing. So these functions are minimum unit of computation. So my responsiveness is limited to the longest of these functions. Okay, so so the challenge which happens in these systems is the following: you may have events which come rarely, they're unimportant, but processing them takes a long time. Okay, maybe you have to encrypt them, maybe you have to run an FFT on them. So these are rare events. They may even be unimportant, and yet their processing takes a long time, and they kill these kind of systems. Okay, because the only way around them is now you will begin to chop their processing into tinier functions, and then you have to worry about calling them in some sequence, and it becomes a royal mess pretty soon. These things handle that nicely, because if something more urgent arrives, the operating system will know, it will just stop that thread. Okay, so that's the pro in favor of thread. The con against thread is that there's a lot more baggage that you're carrying in terms of being able to shift back and forth, whereas these things, literally, you don't even need a formal OS. You can write the system yourself. I mean, if you just think about it, for every interrupt handler, you just put stuff into a queue, and then your operating system, all it does is takes the next thing from the queue, calls a corresponding function. Then when the function returns, goes to the next element in the queue. That's all it is doing. So you can rig a simple version of this in no time, whereas the left one, yeah, there's a lot more complexity involved out there. This right one is actually also easier to analyze. So while it is less responsive, since I can look at how much time each one of these takes, and it's really a finite state machine. If you think about it, this is really a finite state machine in disguise. Okay, so you can, all that theoretical machinery that we learn in either digital logic courses or programming automata courses, you can apply all of these things out there. So next two slides, I basically have pros and cons of those listed out. So threads, the advantage is that the code flow is easier. You can reason about the logic of each thread independently. You don't have to worry about these functions being called in arbitrary order. It is suitable for long computations, they're pointing out, because the OS can preempt it. But going back and forth between threads requires saving all that state, so that context switch is extremely can be extremely high. You also can have complications between threads, like what if this thread started using the radio, and then suddenly an event came and then the OS started running this thread, and this thread also needs the radio, but this guy hasn't released the radio, it is still in the midst of using it. So then you have to keep track of those shared resources. That problem doesn't occur out here, because the other handler cannot run until this handler returns. So it's a lot easier to handle shared resources and all with the threads. Threads also require very high memory. The reason is that each thread needs its own stack. So you already have limited memory, and now you are going to parcel it up and kind of give tiny stacks to each one of these threads. Whereas in the handler case, these are function calls, right? I mean, I have a top level code here, and it's calling handler 1 or handler 2 or handler 3 or 4 in some order. So there is a single stack. In terms of memory resources, threads are more hungry than the handler based approach. So the pros and cons of event driven are exactly the dual. Much more memory efficient because there is a single stack, much lower context switching cost, no need for locking mechanism because the handler does its job and only then returns, and generally more compact code. The cons out here is no preemption, so if I'm in the midst of a long running computation in a handler, tough luck, everything has to wait. Code flow is very unstructured because order in which these events, these handlers get called is dictated by what is happening in the outside world. So you can't really say, oh, handler 1 runs and then handler 2 runs. It depends on how the external world was behaving. And I already made the point earlier, it's not good for long running computation. In particular, rare events which require long computation can kill this system. If the event was very frequent, then you would then in both cases you'll have to worry about it. But the rare event, long computation case causes a lot of problems out here because you are essentially locking the processor there. Okay, so event, thread, and you will see papers like from really top level operating system researchers and all. Threads are evil, events are great, and vice versa. And I mean, there literally are papers with these kind of titles. Okay, so this has been a debate which has gone on for a long time, and there are valid points on each side. Okay, in programming languages like C with operating systems like Linux, you can adopt either style of programming. So I already talked to you about how certain calls result in you blocking. In Linux or Unix like operating systems, you also have something called signals. Anyone ever use signals? Nope. Yeah. Okay. Signals are a way to send essentially events from OS to send events to you, or for one program to send events to another program. Okay. And then there is also a way for you to wait. Kind of say, I'm waiting for event to happen from a set of events, set of possible sources of events. In Linux, it is referred to as poll, P-O-L-L, or select in kind of ordinary Linuxes. Okay, and this one, the event handler, you can implement it yourself. You don't really need an OS support. I mean, if you think about it, it's pretty simple to realize directly. So events and threads. Now it's almost 5 p.m. so let's take our 5-minute break, and then I'm going to go into what are the ways then we structure the code very commonly in these systems. Okay, and so 5 minutes, then we restart. And again, for those who came in late, tomorrow discussion section 4 to 4:50, no office hours. Discussion section will basically go over project ideas. Yeah, so you just that's fine. But I think Leon, you will take the lead on purchasing, getting. Because Lorena isn't here, so I want a single purchase request to go out to that possible. So,
so there's Greece, there's Brian's order, there's mine, and I guess mine doesn't do that. Is this the room for?
No, it's 5127 Maxwell.
Question for the circular purchasing. Do you think they'll support AliExpress?
You will have to buy yourself, and then
in that case,
that's fine.
as
long as there's a proper invoice. Yeah.
Most of these boards, the ESP32s, are mostly sold on AliExpress. So
Amazon has them.
So should I look for alternate options if possible?
Yeah, Amazon has them. I mean, I purchased one before from Amazon, but AliExpress is fine too.
They have good prices.
But rapid shipping is costly.
Yes, but I think the shipping was around like $3, no matter how many boards you order. So
No, but that takes around a couple of weeks. So you'll probably do that. So do the trade-off and see. So I think if you're buying in quantity, even the expected. Seed Studio is another option, but a lot of vendors are selling on Amazon also at somewhat higher prices.
I think the reason this one is best is one of the vendors is Ramos, which I was also getting discounted, so that's why
They're all things. The only American company which is selling USB32-based stuff is
SparkFun has like one state,
but they're both costly.
Yeah, I looked at them. They look worse. They don't even have like shielding or it's just the bare chip. They're on the board. So these look better.
So I filled the form, but I didn't get the PTE. Before I filled it late after the.
Oh, okay. Can you just send me an email and then I'll send you a PTE? Okay. And you did put in your student ID number in the form, right?
Yeah.
Okay, great. Or you must be the last time. Just send me a reminder this evening if you don't get one.
Yeah.
Are you a CS student? Yes. CS. Are you trying to register for CS? Yeah. Okay. Yeah. Oh. So I'll just need to give you a okay. Just send me an email. For sure.
Do you have any questions?
Okay, let's start. So, just one thing, a student from this course's previous offering sent me an email that there's a group here at UCLA who's looking for, there's a funded whatever lab research position for making an embedded system to control an electrostatic cooling system. If any of you are interested, contact me and I'll put you in touch. Okay, back to, the other thing is, if you're interested in more, if you're a PhD student or whatever, going to be doing PhD and are interested in a either hardware or firmware type internship at Google, again, let me know. I can forward you a flyer that they have sent around. This is their hardware platform group, which is looking for summer interns. Okay. Ways to structure embedded software in light of kind of the discussion we have had. So it turns out that there are kind of three common ways that people kind of use. There is the so-called single task approach, then so-called foreground background approach, and then finally kind of the more general case of multitasking. So let's imagine that there is some sort of device you are building, some sort of system you're building, and it has to do a few different tasks. There is a task which needs to happen. There's some sort of a timer which is generating events every 20 milliseconds, and so you can think of it as the heartbeat of the system, and every time that clock tick happens, some special module, we are going to just call it the clock module, must run. So that's one task, one thing that we need to do. A second one is that every alternate tick we need to run some sort of a control module. And then finally I have a few other modules, but they're kind of soft in terms of their timing constraint. There is some sort of a display update we need to do, there is some sort of a input from a human that we need to handle, and then finally we need to log things so that we can do forensics later on if necessary. So if this is my workload, a single task approach might simply use a polling approach out here. So what it may do is we can sit in an infinite loop. I can wait for the clock tick to arrive. So this part could be an event. So wait for the event from the timer. And then since I have to run the clock module every time, I'm going to run that. And then I'm going to check if it is time for control module, I'm going to run that, and then finally I can in some particular manner run the more softer modules. And if you think about this, for this piece of code to do its job correctly, so remember, one module must be run every 20 milliseconds, another module must be run every 40 milliseconds, and the remaining ones we don't really care, they are kind of software. So what it really means is that T1, which is the time it takes to run the module which has to run every clock tick, and the maximum of T2, T3, T4, T5, because I have structured them in a if-else statement, should be less than 20 milliseconds. Okay, so what is happening in this case is that even those rare events like operator input or whatnot, even though they are not constraining my time, they are kind of a bottleneck because I'll have this maximum term sitting there, because once I call that function, then I have to wait for it. So this whole thing is kind of a variant of the event handler approach, and it is suffering from that disadvantage that I'm limited by the worst case, even though it may be happening pretty rarely. So the solution here that is that if you know that one of these functions take a long time, you're going to split them and chain them. So you are going to say part 1, part 2, part 3, part 100, and then kind of keep track of what you had previously done, and the code soon becomes kind of rather messy. So, but if on very low-end systems, low-end microcontrollers and all, this is probably fine for under the resource constraints. Far more common is the so-called foreground background approach. So if you don't have any operating system, you're running on a low-end processor and all, much more common is to organize the system in terms of a foreground task and a background task. The foreground task is actually nothing but the interrupt handler, and it's called foreground because whenever it happens, it has the highest priority. It comes to the top. So the idea is that on the interrupt, I will do the clock module, and then I will also, if it is every alternate interrupt, I will also do the control module. Kind of basically, we are putting all our time-sensitive stuff as part of the interrupt handler. And in the background, I would basically spin in a while loop and repeatedly check whether I could do any one of those tasks and do that. And essentially, because the hardware makes sure that the interrupt handler is given the processor, so it has like a high priority, so it gets the CPU, and any remaining CPU time is just shared between these non-time sensitive tasks. So we kind of decouple time sensitive stuff from non-time sensitive stuff. And I'm showing it in just one particular way, but another way that these systems are often organized is that I will do the time sensitive stuff out here. So let's say oftentimes what may happen is that the clock module may have a time sensitive part and a time delay tolerant part. So what we do is whenever it happens, I'm going to take care of the time sensitive part, and the delay sensitive part I'm going to put it into a queue. So that in the background part I will monitor the queue and work on those later. So the foreground can basically send data to the background through a queue. Mbed has a structure like this. Some of the examples and all that they provide in the operating system are along those lines. So like for example, if you want to do something sensitive like read a sensor sample every millisecond and then collect 100 of those samples and do an FFT over them. Let's say that's what you want to do. So every time the timer fires, you will collect the sample, but you're going to put the sample into the queue, and then the background task will just wait until there are 100 samples, and then it's going to do the FFT. So you kind of try to decouple delay tolerant and delay intolerant stuff in this manner. So very commonly used, and many of the so-called operating systems for low-end embedded devices are really foreground background systems in disguise. Okay, they basically make you write this. If you I mean Arduino and well, Mbed has kind of evolved now, but Arduino certainly in this category, for example. So it's not really a multitasking system and all. So the loop part of the Arduino is basically the background stuff. And when you write an interrupt handler in Arduino, you're writing basically the foreground part. And the setup part is just some initial code. How many of you have done programming in Arduino? Just curious. Okay, so almost everyone. Okay, so you're familiar with, at least those of you who have done, you're familiar with that, what I'm talking about. But basically, those of you who are not, in Arduino, in the IDE, you basically you're allowed to write 3 pieces of code. What happens at boot up time, so that's called the setup. You can write interrupt handlers, and you can write the body, this loop code basically. So those are the 3 things. Okay, so this works for a lot of embedded systems, but the final one is the full-blown multitasking stuff, where we can have multiple tasks, and there is an operating system, and it's juggling between these things, and it's deciding how, using some sort of scheduling policy, moving between these things. The ones which try to share the processor in a manner that timing constraints are taken into account are referred to as real-time operating systems. Mbed, if has many versions of it, is now at version 5.10 or something like that. But original Mbed 1 and Mbed 2 were really foreground background systems. But now Mbed has kind of the full-blown multitasking capability. It has threads and stuff like that and all. So, and even there, I mean, there have been multiple releases. So I just wanted to talk about how Mbed handles multiple tasks. And this is for their older version of the API, but most of the concepts apply. And since they had ready figures for them, so for the older version, so that's what I'm using. So basically, there was a open source operating system called RTX, and Mbed adopted that to as the part of as the core part which is providing this real-time operating system capability. So the main thing it provides is the concept of threads, as we kind of talked about earlier. And in most of these operating systems, and in this case also, these threads can be in several states. So deep down in the operating system, there will be some data structure for each thread, and the number of threads is assumed to be in many cases assumed to be known upfront. That in other cases you can create them dynamically, but that's sort of kind of orthogonal. For each thread, there will be some data structure. This is often called as task control or thread control block, and in there you maintain information about the threads. And one of the information you maintain is which state is the thread in, and for each one of these states, some of these states, there is a queue associated with it. So very broadly, a thread could be in one of 4 states. It could be running, and the number of threads that can be running will equal to the number of processor cores you have in your system. So assuming I have a single processor core, I will have exactly 1 thread that can be running. It may be that I have no thread running, but at most 1. Then I have threads which are ready to run. It's just that I have not given them the CPU. They are called to be in the ready state. So if I give them the CPU, they are good to go. Then I have threads which are waiting for something. So these are threads which have executed an instruction saying wait for an event. So like wait for an event from a timer, or wait for an event from an interrupt on a pin, or maybe wait for an event that another thread will generate. So they're waiting for some sort of an event to happen. And in the waiting thing, there is a queue which may be organized in some manner, let's say according to priority or according to timing constraint or something like that. In the ready side. In the waiting side, there is a set, and then when the event happens, the corresponding thread will move to ready or move to running if the processor was free. Okay, so when the event occurs, the event goes to the operating system. Operating system now has to make a decision what to do. Depending upon the operating system, it may bump off the currently running thread and give it to the new one. So like an event came and it's an urgent event, maybe I'll bump off the currently running thing. There are a variety of policies, but very broadly, one set of policies says I will never bump off the currently running process, currently running thread. I will wait until it gives the CPU up. And the other one is I'm going to bump it off. Okay, so one is called preemptible, the other is called non-preemptible. Okay, so waiting means I'm waiting for an event. Ready means that I have everything that I need. I can run an instruction as long as the processor is given to me. Running is I'm actively running, and inactive means kind of like a zombie state, a dead state. Okay, so you have killed the process, killed the thread, so to say. If I preempt, it will return to ready because it was ready to run. I preempted it. On the other hand, if it gave up the CPU, that will be because it needs something. Okay, and in that case, it will go to waiting.
Does it remember where it used to be in the program?
Yeah, so that's part of the thread state. So that's what that so-called context switching code. It will save all the registers. It will save, including the program counter. So it will save all of that, and that code is fun to write, but it's very detailed. You have to get a lot of things correct. But if you, in the OS courses, I guess they probably make you write. I don't know, anyone done an operating system course? And you did, but you didn't write.
We did not.
Okay. Did you ever write a context switcher? No. Yeah.
context switches that you have to manage the threads.
You have to manage the threads, but not, okay, so you manage this transition,
Yeah,
but not the
yeah.
low-level stuff. Yeah, okay. Yeah. I guess, I don't know, my undergrad days, in my microprocessor class, we had to write that low-level stuff also, but I guess, I mean, unless you are in the business of writing low-level OS code, you'll never need to. So as he pointed out, really the focus ends up being how do you move the threads around, right? The basic thing of what happens, how to save the state, how to restore the state and all are. Okay. So inactive, you can think of it as I no longer need this thread, put it out there, it's like effectively have killed it. Okay, so although there is a possibility maybe I can restart it. Okay, so depending, in case of embed, you can actually create, and I think you can revive a thread also. Okay, but that's those are different. Main thing is that when a thread is running and an event happens, and that event causes one of the waiting thread to become ready to run. Okay, so it could, now there are, at that stage there are two types of systems. One type of system, the so-called non-preemptible systems, all they will do is they will move the thread from waiting to ready and go back to business. Okay, the thread which is running will run, and at some point the thread which is running is either going to die or it will in turn need something. So it will say, I wait for an event. So then it will give the CPU up, and then some algorithm will decide that among the processes which are ready to run, which one should I pick and let it run. So those are the so-called non-preemptible policies. And then the other type is preemptible, which is, say, you know, the thread which was waiting here, and now because of the event that arrived, it is ready to run. It is so super duper important that I'm going to bump off the currently running thread. I'm going to move the currently running thread to ready because it is ready to run. It's just that it's less important. And then I'm going to run that new thread out there. And that's called preemptible. Okay. So non-preemptible, preemptible basically refer to that can the thread which is running, can it be involuntarily moved from running to ready? Running to not running, or running to ready but not running. Right? Okay. Yeah, double arrow means that something goes from here to here, something goes here. So bi-direction thing. You can thread go from running to ready or ready to running. Yeah. Let's see. Am I missing anything else out here? Yeah. One other thing is threads themselves can emit events too. So events, there are basically three sources of events. Events which come from internal peripherals like timers, events which come from external sources like A to D converter or just a pin or a serial port, right? And the third one is a thread may generate an event to send to another thread. Okay, so three sources to consider. Okay, so that's the thread structure. Then, yeah.
One more source, so exceptions. Exception because something.
Yeah, I mean, I'm lumping all of them under events. So exception, software interrupts, all these things are interrupt-like or event-like. Okay, so anything which can happen asynchronously, I'm lumping under. Some operating systems, it's kind of Leonard pointing out, they kind of make a distinction between soft interrupts and hard interrupts and exceptions and all. You'll see all these kind of jargon, but at some level, kind of those distinctions really basically boil down to this notion of an asynchronous event happening. Like for example, in Linux, they have hardware interrupts which cause hardware interrupt handlers to run, and hardware interrupt handlers can then generate software interrupts for other modules. But you can think of them as hardware events and events within the processor. Okay, there are other sources of events. So I guess I said there are events which are, I guess that's what you were pointing to. So events which are happening from external sources, events which are happening from my code emitting events, events which are happening from peripherals, and the fourth one is something bad happening in the processor. Like for example, you attempted to divide 1 by 0. So that will result in a floating point exception. So the processor, or your code tried to access an area of memory which it was not allowed to do, or stuff like that. So any sort of bad condition, exceptional condition, is another source of event which the OS will have to do. Yeah. Okay, so these threads also talk to each other. So like most operating systems will provide variety of ways for the threads to talk and coordinate with each other. So the most basic coordination that you would find is that there are resources which only one thread should be using at any given point in time. And so it's kind of like a room in which only one person is allowed, only one thread is allowed to go there, okay, at any given time. So this problem in computer science is referred to as mutual exclusion problem. That is, there is some state. In our case, typically it would be some resource that we are using, like maybe control of the LCD display. Maybe only one thread should be doing it. If both parties are trying to write to it, the messages will get garbled. Okay, so only when one party gets control of the display, it can print out the whole sentence and then give up the display, and then other thread can write to it. So that thing is called mutual exclusion, and essentially it is an object which is maintained by the operating system, and then it provides you API to share it, and it does so by an API which gives you two function calls, wait and release. So by waiting, you are locking, you are basically saying, I want to enter into this thing, I want to start using this resource. Okay, so this mutex is protecting some resource, like a room or a radio or a display or a whatever, your door lock or whatever, things like that. Wait means I'm expressing my interest, and release means that I'm no longer using it. I was using it and I'm no longer using it. In wait, what happens is there are two possibilities. When a thread calls wait, it's one possibility is that the mutex is free, and therefore the operating system will let me in which case if I was running, I'll keep running. It's immediately I can keep running. But the other possibility is that some other thread had previously done a wait, it had received this thing, so it is now using the resource, and now that thread is no longer running. It is sitting either in the ready queue or the waiting queue for some reason. In which case, my wait will not succeed, so my thread will now go into the waiting queue because it has to wait for this mutex. So, and then the operating system, eventually the other party will run, it will call the release, and then I will be able to enter. Okay, so I kind of have to wait in that case. So this wait release are and there are other operating systems call these functions differently, but kind of the concept is I'm expressing interest, and then after some delay I will actually get to enter the room, and then I exit the room. So mutex. The problem with mutex is that it becomes very painful to do more complicated things with it. What if I have a device which 10 users can use simultaneously in any combination? So like, okay, so how do I express these kind of things? So there are more complicated scenarios that develop, and so for those, most operating systems provide more advanced forms of this sharing control. So the next more advanced stuff is called semaphores, and the main thing about semaphores is that you can think of it as a room with a capacity which is more than one. So you can think of mutex as a room with a capacity of 1, so only one thread can be in it, whereas semaphore is a room with a capacity in this example of 6. So up to 6 threads can enter, but if 6 are already there, the 7th one will have to wait. But otherwise, it's the same abstraction. So for things such as memory or any type of like some sort of buffer and all, or certain sensors. Okay, maybe I have whatever 6 sensors of a certain type, and I can accommodate that many requests. Okay, so semaphore is useful for those. Next up is signals, and I mentioned that Linux or Unix also have signals, so these things are very similar, but kind of the basic idea behind signals is, and unfortunately I think between the lighting and the font, probably very hard to read out here, but signals are basically as a way for me to send a message. So one thread can send a message and the other thread can wait for it. So this is good for coordination. One thread is waiting for the other thread to reach a certain stage. So like for example, think of it like a handover in a relay. The next guy is the thread corresponding to the next runner is waiting for the previous runner to reach a particular goal. Okay, so signals accomplish that. It's basically indicating that one thread has reached a certain state before the next one can advance. Yeah. Pipes can be implemented using signals, or actually Mbed RTOS doesn't have pipes, but it has queues, which are serving the similar purpose. So signals combined with some area of memory can be used to implement pipes.
So pipes are higher level.
Pipes are higher level. Yeah. So signals do not have a payload. Okay, you can just say it is a mere act of informing. It's not actually sending you any content other than saying I have reached that state. Okay.
It's like a notifier.
It's like a notifier. It's basically it's basically just saying I have reached state S. That's it. I'm not able to send you a payload. If I want to send you a payload, then you use a next thing called queues, and internally they are built using semaphores. So look, signals are built using semaphores and mutexes, so they kind of internally form an implementation hierarchy. Okay, so message queue is basically a queue in which will have some capacity, and you can actually put a message in it. Usually message which is basically just a pointer to some data structure, and then you can do a put and a get. And if you do a get and the queue is empty, then you will wait. And if you do a put and the queue is full, again you will wait. Okay. And sometimes get and put may have some additional features. I don't recall whether Mbed does or not, but you can say get but don't wait. Okay. Or put but don't wait. So the idea is if get, but if the queue is empty, just return immediately. Okay, because maybe I'll repeat the last value or something like that. So queues are the next level abstraction, and but in this case all you are allowed as a payload is an int value, like a 4-byte number. Okay, and then finally there is mail queue, which it provides, which actually can have a larger sized payload associated with it, but fixed size. So you can basically say this thread is sending mails to this thread, the other thread, and they are all 10 bytes. So then you kind of allocate that. This whole hierarchy is built up. The final one, which is kind of orthogonal to so mutex through mail are different ways of sharing resources and coordinating. Timer is useful because in these systems you often have to deal with timing related things, like you may want to generate a PWM waveform, you might want to timestamp events, you might want to do all these kind of things. So usually these operating systems provide some significant support for timing, and at the very bare minimum they would have things like start a timer, stop a timer, what is the current time, these kind of functions. So in this particular case there is a timer start, there is a timer stop, but other operating systems have more richer semantics. Okay, in Linux also now there is support for real time. In fact, there is a clock that modern Linuxes provide which give you timestamp to nanoseconds. So you can, and Linux now has an deeper, as part of its kernel, it supports real-time things. Okay, so you can make use of it and do a lot of stuff which previously was only possible in sort of so-called hard real-time type Linux, but now even ordinary Linux kernels can do a fair bit of stuff. So timer and things around time, but usually since these operating systems are designed to run on a variety of processor platforms, they don't make full use of all the capabilities that may exist in a given MCU. So we saw previously in the previous set of slides that there were a lot of different kind of timers and all that are there in the MCU that I was showing. But these timer abstractions probably just make use of one of them. There are all sort of other capabilities that exist in the hardware which you would find it useful to make use of for specific purposes. Like, for example, a very common thing which often we need is to measure interval between two transitions on a pin, or two different pins, or maybe I want to timestamp when a transition happened on a pin. So the problem with this is that if you were to, so one approach would be I repeatedly read the pin, polling. But the problem is that while I'm polling, I may get interrupted by something else. So my timestamp can be totally wrong. If then you can say, okay, fine, maybe I'm going to make that incoming signal to be an interrupt handler. The problem is, since the time the pin action happens to the pin to the time the interrupt handler runs, there is still some delay. Moreover, the software may have disabled the interrupt. So again, you'll have a problem. So most of these MCUs provide another feature called timer capture. So basically you tell the hardware that whenever there's a transition on this pin, you take a snapshot of this timer and save it in a register. Okay, so that you get one clock cycle accurate timestamp. Now, no operating system exposes that. You basically have to write your own code to make use of that capability. So anytime you're dealing with finer stuff, you basically have to get your hands dirty and make use of those capabilities. What the operating systems provide is kind of the things that cover the general cases and which work well across processors. And then things which are very hardware specific, you basically have to dive in.
Does the OS allow you to use this feature?
Yeah, so in these things, remember the operating system is running, there's no protection, unlike your laptops and all where your operating system runs in that supervisory mode, the privilege mode that I talked about last time. In these processors where Mbed is running, everything is running. You can override the operating system, you can modify it, you can do whatever you want. Okay? So totally open, and obviously as a result also very risky, because if you do something wrong, like for example if you start crashing the stack and the stack blows, maybe your some if condition is wrong and you have too many nested calls and all, you'll wipe out the memory and along with it the OS. Okay, so everything is possible here. So that's the risky part. But on the other hand, one way of thinking about these things is you are writing part of the operating system, which would normally in these things in our laptops and all desktops would be referred to as device drivers. Okay, so in effect, there's a statement I read somewhere that a desktop or a laptop is nothing but a whole bunch of embedded systems, and in some senses that is true, because if you think about your laptop, right, I mean there is low-level stuff dealing with radios and keyboard and battery monitoring and a whole bunch of stuff, and these are all individually like embedded systems. It's just that layered on top of it is a rich set of applications which make it look like a pleasant user-facing environment, but deep down there is a lot of what embedded system like programming going on. So short, that's a long-winded answer, but in short, you can mess with hardware registers directly. In Mbed, you can do it in Arduino as well, although most Arduino users don't even know about that, so they don't do it. Okay, let's see. You are allowed to write interrupt service routines and attach them to specific interrupts. So some interrupts are handled as part of the main operating system because they are dealing with some very essential things which the OS likes to grab. Like for example, almost every operating system needs one timer to do its job. So it will grab that, and in the documentation it will tell you timer number 0 is being used by the operating system or something like that. Okay, but then a lot of other hardware resources are free for you to use, and for those you can write the ISR. There are certain restrictions when you write interrupt service routine. Okay, Mbed imposes them, as would any other operating system, as would Arduino. Okay, firstly, your interrupt service routine must return very rapidly, because if it returns very slowly, then the whole system hangs, and you cannot afford an embedded system from hanging, right? So it in turn has consequences. You cannot use a mutex or a semaphore. Or why not? Can block, right? I mean, because the resource might not be free. So you're not allowed to use mutexes or anything which is based on mutex. Wait is not allowed. You cannot say wait for interrupt, because maybe you'll wait forever or a long time. So that's a bad idea. In fact, the compiler would check and basically give you a error if you were to do it. Any method which has a timeout, if it has a long timeout, again you have a trouble. So they actually all set to set it so that there is no possibility of a wait. So you cannot say write to this device but wait until it is ready, because it can take a long time. So ISRs have to be optimized for doing quick, dirty job and return rapidly. If they fail to return, all sort of problems will happen for rest of the system. Okay, so some of the key questions underlying the multitasking approach then happens is really management of this structure. When to move tasks or threads from one state to another. So, for example, multiple threads may become ready when an event occurs, because they were all waiting for the same event. What should I do? Which one should I run in that case? The considerations for that may include timing, may include power, may include importance, may include availability of resources like radio and other things. So there are a variety of criterion that the operating system can use to decide which of the several ready threads to actually run. Okay, maybe the most important one, maybe the one whose deadline is the closest. Could be various ways you can think about it, and next slide set goes into that from a timing perspective. When to stop a running task. So I talked previously that there were two approaches. One is the preemptible approach, where I'm allowed to stop a currently running thread and give the processor to some other thread, even though the currently running thread was happy to run more. Okay, and then there is a non-preemptible case where we say that the currently running thread is allowed to run until it voluntarily gives up the CPU. Do you see a problem with the latter policy? Bugs, right? I mean, what if it just goes into an infinite loop? So that's a problem. But so at the very least, there would be something which would prevent that from happening, from lockup from happening. There's a special timer that many processors provide, and so does the platform. And it is called a watchdog timer. So a very common problem in embedded systems is that the software hangs. Now, unlike our laptop where we can curse and all and then do a hard reboot, we can't do that out there. So the job of hard reboot there falls onto this watchdog timer. And the way the watchdog timer works is, that's a timer which starts counting down, and when it hits 0, the system will reset. And it's the responsibility of the software to go ahead and reset the timer before it hits 0. Okay, and so if the software hangs, presumably it will fail to do so, and therefore the system will reset and kind of restart from scratch. Okay, so watchdog timers are kind of the savior there. Back out here, what if so when to preempt a running task? It may even be that you might want to preempt even though no event has happened. just out of fairness. Like you may say, this thing has run, this thread has run long enough, and I have other threads which are ready to run, maybe I should give the CPU to them. So fairness could be an additional criterion as well. What if there are multiple CPUs? Then there could be multiple threads that could run simultaneously. And then in all of this, you have to take into account the cost. Context switch has a cost. You have to save state and stuff like that. All sort of communication costs and all. One has to kind of worry about these. Now, all these things are collectively complicated enough that if you need multitasking, it's probably not something you should rig on your own. You should use a properly designed and implemented operating system. There are excellent choices. Mbed is one, but there are a whole bunch of others. There's something called FreeRTOS. There's something called Newt from Apache, the same people who made Firefox, and kind of a tinier version of it called MyNewt. There's something called Zephyr, which is from Linux Foundation. There are a whole bunch of these things exist. And Mbed itself is also coming out with Mbed Linux, which is for the A series ARM processor. So the Mbed OS that I talked about is for the M series, the one where there is no protection, everything kind of runs in a single address space. But there is an Mbed Linux coming, which is meant for the A series processor. So there are a whole bunch of choices, and I guess at some level they're all very similar. Okay, it is really more about the community and the community support and the tool support, and are there enough hardware choices and all available around it, which really dictates things. There is an operating system in the same realm as Mbed called Micro-C OS, and it is free for non-commercial use. A very nice thing about it is that there is a book you can buy on Amazon or wherever, and which basically line by line goes through the entire operating system code, describes what's happening. It's a great way to learn operating systems because it's not complicated like Linux. It's a simpler one. It's like this Mbed thing, and yet it's fully documented, describe everything. You can modify it. So if you want to learn about an OS, it's a great resource. There's something called FreeRTOS, which Amazon uses, for example. It's a pretty robust thing. There's something called NutOS. There's something called TinyOS out of UC Berkeley. There is it's kind of dead at this point. There is something called Contiki, which is out of Uppsala University in Sweden, very popular in Europe. So there are a whole bunch of these things that exist, and there are different communities and all. Mbed, the nice thing is that it's blessed by ARM, so ARM is throwing all its resources. It has all these nice browser-based goodies and stuff like that, which makes it, I think, my view, it should be your top 1 or 2 choices when you are looking at operating system in this category, just because of the rest of the support infrastructure that exists around it. Okay, so that brings me to the end of this. So we basically saw kind of notion of software modules, that it's really all about sharing the processor hardware, and the question is really how do you share. This is the topic of the next lecture in terms of scheduling and all, and then how do we organize this code and this kind of single task, foreground, background, and multitasking. So these are kind of your choices, and around these concepts there are a whole bunch of open source and commercial things that exist. So let's stop here, and we'll see you guys on Tuesday. Oh, sorry, we'll see you tomorrow. Sorry, I hope I remember to come.